Welcome back, Focus Learners, to another explainer where we take complex technical concepts and break them down into crystal clear insights. Today, we're talking about the high-stakes, incredibly unforgiving world of writing smart contracts in Solidity. You see, when you deploy a smart contract to a blockchain, you're doing something pretty profound. You are deploying immutable code. It literally cannot be changed, it doesn't get a quiet patch on a Friday night, and it often holds real, serious economic value. We're talking millions, sometimes billions of dollars in Ether, tokens, or NFTs. With stakes that massive, how do you defend your code? Well, today we're going to master a tool that serves as your ultimate last resort defense mechanism. To really understand why we need this kind of defense, we just have to look at history. The infamous DAO hack back in 2016 drained $60 million, all because of a single reentrancy vulnerability. In traditional software, if a bug like this pops up, a developer just pushes an emergency update and the system keeps humming along. But in Web3, immutability is the whole point. It guarantees trustlessness. But man, it also creates a brutal constraint. If a flaw exists, it will be exploited. That makes runtime validation your absolute first line of defense against catastrophic loss. You literally need mechanisms baked directly into your contract that are constantly verifying reality.
Okay, let's dive into this. Section 1, the smart contract panic button. So let's define the assert function. It's a state-reverting statement used specifically to check for internal invariants. Now, what does that actually mean in plain English? An invariant is just a property of your contract that must always hold true regardless of what the user does or what the external state looks like. Think of it as a fundamental truth, the actual laws of physics for your program's universe. When assert is called and the condition evaluates to false, it immediately halts execution and reverts all the state changes you made during that transaction. It is, strictly speaking, a panic button. It's meant entirely for the internal machinery of your code. You absolutely do not use this to check if a user typed their password wrong. You use it to check if the laws of physics in your smart contract have suddenly broken.
Now, what's really interesting to see here is the sharp contrast between what's considered invalid and what is straight up impossible. In normal software development, we deal with the invalid all the time, right? A user tries to withdraw more funds than they have, or maybe they send an incorrect parameter. Those are completely expected edge cases. But assert? It doesn't care about the invalid. Assert exists strictly to handle the impossible. If an assert statement fails, it means an invariant that you, the developer, believe to be mathematically certain has somehow been violated. It basically means your contract has a fundamental logic bug.
Let's move on to Section 2, handling the impossible.
The security mindset in smart contract development can basically be summed up in 4 words: fail fast, fail loud. Because blockchain transactions are atomic, meaning they either execute entirely or they don't execute at all, reverting early is incredibly important. If an impossible condition is actually met, assert embodies this fail-fast principle perfectly by halting the transaction immediately. It stops any partial state changes from saving to the blockchain. And this is absolutely crucial, because partial state changes are exactly what leave a contract in an inconsistent or highly exploitable state. Much like the reentrancy attack that drained the DAO. And this brilliantly illustrates exactly what we mean. Imagine a scenario where, right after a token transfer is completed, a user's balance suddenly evaluates to a negative number. Under correct arithmetic, this should be flat out impossible. If a line of code reads assert balance greater than or equal to 0, and that statement somehow evaluates to false, it proves beyond a shadow of a doubt that the contract's fundamental arithmetic or logic flow is totally broken. Something bypassed your checks. When this happens, the contract correctly panics, completely shutting down the transaction to protect whatever assets are left.
All right, moving to Section 3, gas, penalties, and panic codes.
So this is perhaps the single most defining characteristic of the assert function. When an assert fails, it doesn't just politely revert the transaction and hand the user their unspent gas money back. No way. Instead, the EVM brutally penalizes the failure by deliberately burning every single drop of gas left in the tank. Think of it as the ultimate unforgiving parking ticket for a broken universe. Now, you might be wondering, why such a harsh, absolute penalty? Well, the philosophy behind this deliberate gas burning is super specific. First off, it loudly signals a critical, catastrophic error. It is essentially the EVM's way of setting off the loudest alarm possible. Second, it heavily discourages developers from using assert lazily for just routine input validation.
Doing that would unfairly punish users for simple, everyday mistakes. And finally, because an assert failure represents a severe programmer error, a literal bug in the contract itself, it completely aligns with the principle that the system should crash as hard as possible to prevent any further execution of compromised logic.
Let's move forward and see how this builds into modern debugging. In Solidity versions 0.8.0 and higher, an assert failure doesn't just silently burn gas. It actually throws a specific panic error code. When the panic button is hit, developers get a hexadecimal code telling them exactly what impossible thing just happened. So a 0x01 is a standard manual assert failure. A 0x11 tells you that an arithmetic overflow or underflow occurred. 0x12 means someone somehow managed to divide by 0, and 0x32 flags an array index out of bounds. These codes are just invaluable because they instantly point the developer to the exact type of invariant that was violated.
Which brings us to Section 4, Evolution in Solidity 0.8. If we look at the history, we can really divide the use of assert into two eras. In the Wild West days, before Solidity 0.8.0, arithmetic operations didn't actually check for overflow or underflow by default. Because of this, developers had to manually write assert statements all over their code just to guard against really basic math errors. But in Solidity 0.8.0 and beyond, safe arithmetic is checked by default by the compiler. This was a massive paradigm shift. It basically means that today, assert is largely unnecessary for basic math overflow checks, which frees up elite developers to reserve this incredibly powerful tool strictly for complex, high-level invariant checking.
Section 5, Best Practices and Advanced Patterns. All right, here is your rapid-fire checklist for using assert. First, use it sparingly and only for internal invariants. Remember, every assert costs gas to evaluate, even when it doesn't fail, so overusing it just makes your contract expensive to run. Second, use it to verify state after complex modifications, like checking that your total supply perfectly equals the sum of all balances after a massive batch mint. Third, and this is absolutely crucial, never use assert for conditions that can be triggered by users. Masking a simple, expected user error with a catastrophic panic code is a major code smell. Finally, document your invariants. Leave explicit comments explaining exactly why this assert should mathematically never fail. That is a massive help for any future auditors looking at your code. Beyond just standard runtime checks, assert is literally the bedrock for advanced security tooling. If you're using tools like Foundry for fuzz testing, well, those tools work by aggressively throwing thousands of random inputs at your contract, specifically trying to break your assert statements. Furthermore, tools like Certora use formal verification to mathematically prove that your assert conditions will hold true across every single possible state of the universe. In these advanced patterns, assert isn't just a runtime guard, it's the very definition of your contract's core security properties. So the crucial point is this. Assert is built for mathematical certainty. It is your ultimate panic button. It loudly declares, this should be impossible. And if it's false, the contract itself is fundamentally broken. It burns all gas because a violated invariant means a bug exists, a bug that absolutely must be hunted down, isolated, and eradicated long before the code ever reaches a mainnet production environment. We've covered the mechanics, the harsh penalties, the panic codes, and the core philosophy behind the most uncompromising validation tool in Solidity, which leaves us with this final thought to ponder as you head back to your code editors. If your contract's assert fails today, are you prepared to fix the impossible? Thank you so much for joining me for this explainer. Focus learners, keep validating, keep building securely, and I'll see you in the next one.